Welcome back to an intuitive introduction to probability. In this lecture, I want to show you a first example that's a little more complicated. Calculate the probabilities there within a spreadsheet, show you how we can easily do that. And then I want us to take a first look at the concept that's very important in probability called independence, or also sometimes statistical independence. So let's look at the sum of two dice. We now want to roll two fair dice. And I care about the sum. Those of you who like gambling may know the game of craps, and that's where this is exactly important. You want to roll two dice. So what are the possible outcomes in the sum of two dice? Yeah, 1 plus 1 is the smallest number, that's the 2, and it goes all the way to 12. 6 plus 6 is the largest sum. So the basic outcomes in that sum is 2, 3, 4, 5 all the way to 12. Together our sample space, capital S. And now we can think of events. What's the probability of an 11 and a 12, or a 12, or what's the probability of a 7? Let's now move over to a spreadsheet that I've prepared for you, where we can look at the possible combinations and the probability of the sums that are possible. So here we are at our spreadsheet, where we want to look now at the sum of two dice. So here in the left table, I have in the left column the 6 possible numbers that the first die may show. And here in the top row, the 6 possible numbers that the second die may show. So 6 times 6, notice here we have 36 combinations. And in the table, I wrote for you the sum of the two dice. So here 1 plus 1 is a 2. Here 3 plus 1 is a 4. Now notice the different numbers show up different many times. There's only one way to obtain a 2, 1 plus 1. But for example, there are 3 ways to obtain a 4. There are also 3 ways to obtain a 10. And so this now shows that these probabilities will be different. We have 36 possible combinations. So now here on the right, I looked at the 11 possible sums, 2, 3, 4, 5, all the way to 12. And in this column called counts, I wrote down how many times does the number on the left, the sum, show up in that table. The 2 only shows up once. The 4 shows up 3 times, just like the 10. And notice now, the most common number is the 7, 6. There are 6 combinations to roll a sum of 7. 6 plus 1, 5 plus 2, blah blah blah, until 1 plus 6. Since we have 36 combinations, in the next column I calculated the probability of the 7 numbers for you. 6 out of 36. 1/6 is a probability that the sum will actually show a 7. This is the number that's most common, and those of you who like to play craps, you of course know that. 2 and 12 are the 2 least likely numbers. Only 1 in 36 chance for each of them. That's less than 3%. So we see here the numbers are different, but by counting the possible combinations and the total number of combinations, we can calculate the probabilities. This sums up the discussion of the spreadsheet now. I will now return to the slides, summarize what we just learned, and alert you of some dangers. What have we seen? The sample space has 11 elements. And here's now a popular mistake that I see a lot from my students. They think, oh, we have 11 possible numbers, so the probability of all of them is 1 divided by 11. But we just saw in the spreadsheet that's not the case. Why? Because there are several ways to get a 7, 6, 1, 5, 2, but there's only one way to get a 1, which is a 1, 1, or there's only one way to get a 12, 6 plus 6. So here's a danger that people sometimes think, oh, my sample space has that many elements, the probabilities are all 1 divided by them. That's here not correct. The assumption that all probabilities are the same, that's not correct. So how can we use that classical probability definition to obtain these probabilities? That requires us to take a different look or a different view of the problem and define the outcomes and the sample space differently. Instead of summing them up, let's first look at the pairs. First die, second die. What are now the possible outcomes? 1, 1, 1, 2, 1, 3, 4, 4, 4, 5, 4, 6, 5, 1, all the way to 6, 6. Now we see our sample space has not 11 numbers, it has actually 36 pairs. Number on the first die, number on the second die. 6 times 6, 36 combinations. And they are now all equally likely. The probability of 1, 1 is the same as a 2 on the first and a 5 on the second. And so now here I can use the classical probability definition the way we saw it in the last lecture. 1 divided by 36. Now there's a little more work to think about what's the probability of a 4. A 4 has 3 ways as a sum of occurring. First a 1, then a 3, first a 3, then a 1, or a 2, 2. So there are now 3 of these pairs that sum up to 4, 3 divided by 36, and that's exactly the probability that we previously saw in the spreadsheet when we saw those 3 combinations, 3 in 36 or 1 12th. Now let's look at a different way at calculating these probabilities. Notice the following. When the first die rolls and shows up a 1, that does not affect the second die. It's not like the first die calls up the second die and says, dude, I showed a 1, you better don't show 1 because otherwise the dumb humans get confused. No, the probability of a 1 is still the same as it was before I rolled the first die. So that means the outcome of the first die does not affect the outcome of the second die. This is the concept of independence or statistical independence. More generally, 2 events are called independent if event A occurring or not occurring does not affect the probability of event B occurring. Why do we like this concept? Because now it's very easy for me to calculate the probability of the intersection of 2 events. Because now, if A and B are independent, the probability of A and B, A intersected with B, is just probability of A times the probability of B. And now I can use this with my 2 dice and ask what's the probability of first a 1 and then a 5. Oh, probability of a 1, 1 in 6. Probability of a 5, 1 in 6. 1 6 times 1 6 is 136. And so now I can finally show you a second way of calculating the probability of a 4. A 4 again happens if you see a first a 1, then a 3, first a 2, then another 2, first a 3, then another 1. Those 3 basic outcomes, or if you want to think of them as single outcome events, are disjoint. That means I'm allowed to add the probability of a 1, 3 plus a probability of a 2, 2 plus a probability of a 3, 1. Each of them now I can calculate via my multiplication rule. 1 6 times 1 6 for the first pair, the same for the second pair, the same for the third and last pair. So I get 1 on 36 plus 1 in 36 plus 1 divided by 36, voila, we are back to 3 divided by 36, 1/12, the number we saw in the spreadsheet. And that already brings me to the end of this lecture. What are the takeaways? In that very simple example of the sum of 2 fair dice, we already realized we have to be careful in defining the sample space. Because that later helps us or with calculating probabilities or makes calculating probabilities a little more tricky. I gave you a first look at a concept that's very important in probability, the independence of events, and I showed you a cool consequence of that concept, namely the multiplication rule for independent events. We will see this in action in future lectures, so I hope you will be back for more fun with intuitive probabilities. Thanks for your attention.